Okay, so let's work on 6-1. So I put 2 videos here. Let's start with the PowerPoint. The sections that we will cover today will be the standard normal distribution, real applications of normal distributions, which I'm going to give you calculator commands for them. So the sections that we're going to cover are 6-1, 6-2, and 6-4. So these are the ones that we will be covering. I will put the others PowerPoints up as of optional if you want to go over them, if you feel interested to read more about it. But for the curriculum of the course, 6-1, 6-2, and 6-4. Okay. So unfortunately, we don't have time to go over each worksheet for chapter 5. So I want you to do it and maybe ask me your questions at the end of the class if you have any for any chapters. So chapter 4 was, because it was the beginning, I dedicated one whole day to the worksheets. Okay. Key concepts. So we're going to talk about a standard normal distribution. For a normal distribution, let me show you. This is going to be the curve of a normal distribution where it's bell-shaped, it's symmetric. In the middle of the set, you have mu. It's a standard normal distribution if mu, the average, is 0 and sigma is 1. So a standard normal distribution has a mean of 0 and a standard deviation for the population to be equal to 1. Okay. In this section, we're going to develop skills to find areas, which is the same thing as probability under these curves and graphs, and find the z-scores correspond to the areas under the graph. So I hope you remember z-scores a little bit. So I'm going to give you a lot of calculator commands from this point on. This is if anytime you see a bell-shaped symmetric graph, you know it's a normal distribution. Mu is in the middle, the average for the population. If mu is 0, it's a standard, and sigma is 1, is a standard normal distribution. Okay. Uniform distribution would be something like this, where you have all equal, it's not a curve, it's just like a rectangle. Uniform distribution, area under the graph is 1, so always area under the curve of normal distribution or uniform distribution is 1 because it's the same thing as the probability. Anytime you're dealing with area under the graph, it's the same thing as probability, and the sum of all of them is 1. Okay. Uniform distribution is in form of a rectangle, and the values is spread evenly over the range of possibilities. So let's just look at this question. During certain time period at JFK Airport in New York City, Passengers arriving at the security checkpoints have waiting times that are uniformly distributed between 0 to 5 minutes. So when it says uniformly distributed, you know it's going to be in form of a rectangle. Between 0 to 5 minutes is uniform. So that means it's a rectangle. As illustrated in the next page, you will see. So the question is, so if that's 0 to 5, you always know that area under the curve is 1. So you can find the possibility of arriving at any minute and so coming at 1 minute and waiting for the flight. So in order, so you know this is 5. If you didn't know what this one is, you knew that 5 times p, which is the probability, length area of a rectangle is length times width. So you know that length times width is area of this rectangle, and it's equal to 1. Length is 5, width is p, equal to 1. In order to find p, you divide both sides by 5. P is 1/5. If you use your calculator, you see it's equal 0.2. So that's why you know that this width here is 0.2. So then all of the different possible waiting times are equally likely, and it's 0.2. Okay. This is a continuous variable, the time, weight, height, distance, any measurement basically is a continuous variable. That's why you could have 1.23456 minutes. So it's not exact countable. As you see, this is one out of infinitely possible numbers between 0 to 5. So that's why this is continuous. Okay. So let's just do this problem. Given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So what does the word at least 2 minutes means? Do you agree that means 2 or more? At least 2 minutes. So that means what is the waiting time? Arriving, so it says find the probability that randomly select has a waiting time of at least 2 minutes. So it means 2 minutes or more. So and at max is 5 minutes, so 2 minutes or more. What would be the area of this rectangle right here? You know the width, you know the length. Email that, chat it with me. Whatever is the area under graph here is the probability of 2 or more minutes. 2 minutes or more. Okay. So that's, let's see if anyone got it. Excellent to those who got it right. So you would say, you would say length is So length is 3. Width is 0.2. So 3 times 0.2 is 0.6. Okay. Point 0.6 is the probability, so it's 60%. Again, 3 times 0.2 is 0.6 is 60%. So probability of waiting at least 2 minutes is 0.6, which is equivalent of 60%. Okay. So standard normal distribution. So standard normal distribution with a parameter of mu equal to 0 and sigma equal to 1. So that's only the case where having mu equal to 0 is when we write it in forms of z-score. But in general, so this is for standard where you do it with z-score, mu is 0 and a standard deviation is 1. But in general, just normal distribution itself, normal distribution could be mu here, any mu, and sigma is the jumps. So, and it's symmetric. So it doesn't have to be 0 and 1 when it's normal distribution. Okay. And the area under this density curve is the same thing as probability. And the total area is 1. So the total area under this curve, this density curve, is 1 total area. And then any chunks of area, no matter if it's everything or nothing or whatever. So any area, from now on, please keep in mind, area is the same thing as probability. Area is the same thing as area under the curve is the same thing as probability. So we're going to see that. Okay. We're going to be using technology. So we are not using table, and I'm not asking for table at all, and I don't want you to use table, so just technology. Okay. So we can find the area to the right, area to the left, or area in between using our calculators. Okay. I want someone to read this example, please. Any volunteer?
I'll read it.
Go ahead, please, Andrew.
Example, bone density test. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these test results meet the requirements of a standard normal distribution.
Thank you. So they are normal, and then given that mean is 0, their standard deviation is 1. So it's a standard normal distribution. Thank you. A randomly selected adult undergoes a bone density test. Find the probability that that person has a density test score less than 1.27. So right here, we're gonna use our calculator. Anytime it says find the probability and you have a bell-shaped density curve, so it says test score is less than 1.27. So you wanna find the probability where the test scores, whatever you just let them to be X. You could write Z in this case, but you can always safely write X. So X to be less than 1.27. It doesn't really matter if you put the equality here or not, but less than 1.27. To find this probability, when X is given or Z is given and you want to find the probability, this is going to be the same calculator command you also use for the next section. So you're going to use normal CDF. Normal CDF is our friend for chapter 6. Then you're going to put the lower limit. You're going to put the upper limit. You're going to put mu. And you're going to put sigma. So lower, upper, mu, and sigma. So normal CDF, lower, as you see here. So I want you to start building your own curve, even if the picture is not shown. So remember that you want to find the area. So you're going to say it's a standard testing. So you know mu is 0 and sigma is 1. You can write it underneath that sigma is 1. Because that's a bone density, and in the previous page they said bone density has a mu of 0, sigma of 1. Then it says less than 1.7. If this is 0, this is 1, 1.7 is probably somewhere here. Less than 1.7 means below. Do you all follow so far? So you don't know where that below is ending. It's going forever in that below side. So I can say, I imagine that it's a very, very small number. So I let it to be negative 999. So I don't know where my lower is. So I put negative 99. My upper stops right here at 1.27. Mu is 0. So I put 0, comma, 1. You close it. So let's review it. You want to find the probability given X or Z. It's less than, you need to first mark your graph with mu and sigma. Less than 1.27, you eyeball 1.27 and you say less, so it's going to be below. It's never stopping, it's going forever on the left side, so you say probably is a very, very small number, negative 9999. So with a couple of nines, that reassure that it's a very small number. So lower, negative 999, upper, 1.27, 0, and 1. So now let's put it to our calculator. Ready? Let me go to my calculator. And you all grab your calculators too. Let me clear stuff from yesterday. Okay. So where do you think I'm gonna find normal CDF? If you practiced yesterday's lesson. Yes, excellent. So second distribution, second vars. Do you see right below here, you see the key history, but vars is the red one right now, the one that I clicked on. Second vars is distribution. And the second item right there is normal CDF. If your calculator has a layout of lower, upper, mu, sigma, perfect. If not, then you use parentheses. Lower, -999, couple of nines, whatever you are your favorite number of nines, but very small, so you put negative. Actually, let me put negative using this. Okay. Upper 1.27, because it says less than 1.27, so you stop at 1.27. Mu is 0, sigma is 1. If your calculator doesn't have that layout, so you would normal CDF like here, open a parentheses, -999, this is lower, 1.27, that's upper, mu is 0, sigma is 1. So, and then close the parentheses. Here we go. 0.8979 and so far. That's the probability. Yeah, -1, 10 to power 99 is a good lower as well. So as long as you show very small negative number, then that's fine. Okay, so that's the probability. Probability that you randomly select someone, you randomly select an adult, that has a bone density less than 1.27 is about 90%. About 0.9, you could write a 0.898 or about 0.9 or 90%. Okay. I want you to be able to also write this conclusion sentence. Probability of randomly selecting someone that has a bone density less than 1.27 is this. You can always use the question to help you form your last sentence. Okay, and do you see here the area they have on their graph? 0.898. They use table, we use calculator. Ours is much more accurate. I mean, we had a very, very close number to this one, but always calculator is more accurate. Okay. So let's do, these are with table, forget about them. Okay. They wrote the conclusion as well. The probability of randomly selecting a person has a bone density of below 1.27 is 0.898. Okay. Or 89.8%. Okay. So using the same bone density test, so all of you grab pencil, paper. Using the same bone density test, please do this one with me. You will not just learn by watching me doing it. So using the same bone density test, find a probability that a randomly selected person has a result above -1. Step 1, you always start with the curve. In this case, you know that this is a bone density. They mentioned mu is 0, sigma is 1. I want you to mark where you think is -1. And then I want you to mark and highlight where you think is above -1. Then I want you to write normal CDF of what to mu and sigma. Use your calculator and get the number out. So start with highlighting and then putting normal CDF, use your calculator, send me your answers. Is it a good deal? So let's do that. Mark, so you know this is 0. Think eyeball where -1 could be. Highlight above -1, so there's no stop, you go all the way above. And then I want you to fill in all 4 spots here. Lower, upper, mu, sigma. And then I want you to use the calculator to find the probability. Okay? Find them all. Excellent. The right answer. So I'm looking for more answers to come. So write normal CDF. Where does that start? Where does that end? If it's a very large number, pick your favorite large number, like 99999 or 10,000, 1,000. And then mu. Yes, Shelby, that's right. Great. So just put it to your calculator now. Great job, John. Great job, Tammy. Excellent. Shelby, is that an answer or? Okay. So another few seconds and we'll do it together. So here was the graph. Mu is 0. Sigma is 1. -1, if this is 0, so -1 is a little bit below. If this is the curve, above -1 would be this. You just need to roughly graph it, but please graph it. Without graphing, it's very difficult to get right answers. So then you go normal CDF. This is what I want you to write on the test for me. You start from -1, going up to, let's say, 999. And then mu is 0, sigma is 1. So you put that to your calculator. So now let's go to the calculator and put that in the calculator. So here we go. So we go second vars, normal CDF, lower. In this case, it starts from -1. Going all the way to, let's say you don't know the upper, so a couple of nines of your favorite, 0, 1 pace. 0.8413. So the probability you randomly select an adult that has a bone density above -1 is 0.84 or 84%. Questions? So please privately send me in the chat if you understood the calculator command. Say I got the command, or yes, or something. So I just want to know, or no, so I can help you. You say I need more help, then I guide you right here, because we're going to use this command for the entire chapter. Okay, I got a lot of I got it. Any no's? Any great? So I'm just seeing yeses. I'll be happy to also answer no's. Yes, we can. I will go over it one more time. Okay, great. So to find the command, you go second, vars. You never use normal PDF for this course. You never go PDF. You remember yesterday we had binomial CDF and PDF. That's different. But now we are just using normal CDF. Normal CDF, never normal PDF for this course. And then you go lower, then upper, then mu, and then sigma. And then close the parentheses. If you're using parentheses. If you're just entering them, you just enter them. Let's do another example. Okay. So here we go. Oops.
Coffee full of love. That's what she said.
Okay, so Mustafa, I don't get your question here. What is it? So yeah, upper limit could be any large number if it's not a stopping. So as you saw, depending if you're stopping at the upper, then you're gonna have a -999 for the lower. If you're starting from a number and going up, then your stopping number would be 999. So depending which direction you're going to. If that makes sense. Sigma and mu, no, it's not typically one. In this section, they are talking about a standardized where it's Z and bone density, but in general, mu and sigma could be anything. Let me see what happened here. 5-1. Give me a second. The PowerPoint disappeared. Let me open it. Okay. Where were we? Right here, I think we were. No, we passed that. We were here. Yeah, we used our calculator here and we got 0.841. You don't need subtract from one or other because they use table. Using your calculator, you don't need that. So here we go. We conclude that the probability of randomly selecting someone with a bone density above -1 is 0.8413 or 84%. Okay, now let's do this one. A bone density, this is one more time reviewing the same thing. A bone density reading between -1 to -0.25 indicates that the subject has the osteopenia, which is some bone loss. It's if the person has a bone loss. Find the probability that a randomly selected subject has a reading between -1 to -2.5. So what I want you to do, I want you to mark the graph. So always start with mu and sigma. So this is a rule. Mu and sigma. It's about bone density test still. So they said mu is 0, sigma is 1. Because it's a standardized. We go to the next section, it could be anything, mu and sigma. So you mark whatever is mu and whatever is sigma. Between -1 and -2.5, I would say eyeball and say where is -2.5, where is -1. Oops. Graph a bell shape. Between them, so here we go. So now I want you to find, you would say normal CDF. What is lower? What is upper? What is mu? What is sigma? So put it in here as lower, upper, mu, and sigma. And then send me your answers. Lower, -2.5, upper, -1, mu, 0, sigma, 1. So use your calculator, everyone, and please put this in and tell me what you get. Great job. I'm getting already right answers from some of you. I'm doing it with you. So second distribution. Oh. Every time you type something wrong, you can just say second mode. That makes it quit. Second distribution. Normal CDF. Lower, we said -2.5. Upper, -1. Mu, 0, sigma, 1 again in this case. Awesome. I'm getting... No, lower was -2.5. Okay. Is there anyone here that needs more review of the calculator command before we move on? So there is a name for actually, let's just review that part later. But anyways, so the area to the left, the area to the right, or the area could have been in between, and that's 0.5125, 0.5, yeah, 0.1525. Okay, great. Yes. So great job, everyone. So, and then same thing, you just say probability of between less than, greater than, and so forth. Okay, now I want you to, we are not talking about critical values for this course. If you see it on the homework, let me know. If they ask you to find critical values, I will normally eliminate such questions, because when you are using your calculator throughout the course, you don't need critical values. Critical values are used when you're using table, but when you're using your calculator, then it's not helping. So we don't need to find that. Okay. So now, sometimes, here is another thing. Sometimes the area is given, and then you want to find the z value. Let's just practice that one as well before we move to the next section. So let's say the area of here. Let's say, look at the first graph. Let's say they tell you that the area under the curve is 0.1587, or the probability is 0.157, and they ask you to find z-score. Means opposite of what you were doing. The calculator command for that is on the calculator. Let me show you first. So you go to the calculator. On the second distribution, do you see inverse norm? Normal CDF was what we used. Now if you have the probability and you want to find the z-score, or you want to find the x, you use inverse norm. You put the area, it's always area of lower. In the previous case, what was that? 0.15. Can someone read that to me? Was it 0.15? Say it, because I don't see your chat. So you always put the area of the lower here, and then mu, and then sigma. So it's inverse norm. You put 0.1587, 0.1587, and then you say mu is 0, sigma is 1. Always area of the lower side. And what gives this out would be the z-score associated with that. And that's -1. So they say the z-score, because you did the opposite now. Now you find a z-score or x value depending to what we have. So, and if you go here, you see that was -1. Associated with this probability was -1. So we practice more of that in the next section. -2.5 is the other one. So if I put 0.0062, so do you see this one? If I put this probability, it's 0.0062. So if I go to inverse norm, what did I say for the area? 0.0062. Did I say that? Okay, 0 and then 1. If your calculator doesn't have the area, so then you would say area, comma, mu, comma, sigma. So that would be 0.0062, comma, 0, comma, 1. And that gives -2.5. So, oh, I see. Your calculator, Tammy, is pretty advanced because it says left or right or center. So I would say we are using left when we say lower. So, or if you are using the area of upper, you can use right. Not every calculator has that. So for that reason, we always use area of lower, which is the left on yours. So everyone, please try this one, inverse norm, 0.0062, comma, 0, comma, 1, and see if you have the same outcome as mine. before we move on. Okay. So now let's go to 6.2. Let's go to modules 6.2. Open. Okay. Okay, here are the key concepts. In this section, we're gonna do the same thing as we were doing, but it's gonna be different means and standard deviations. So same calculator command, same concept. So I think they separated it in two sections because they are using table. But since we are using calculator, I would say these two are the same thing. Okay. So you don't need the conversion formula because you are using calculator, but I always put these here if in case. You want to know that you can always go from non-standard normal distribution to a standard with the conversion of z. Given x and convert it to z. Okay. So can someone please read this one? Heights.
I can read it.
Thank you. Go ahead, please.
What proportion of men are taller than the 72-inch height requirement for shower heads? Heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a shower head at 72 inches.
Thank you. So as you see, designing shower heads, doors, car doors, so they need some sort of a statistic to know where the mean of tallest and shortest people are. So depending to what they are designing, they need to find something that majority of population fit. So height of men are normally distributed. Anytime you see normally distributed, okay, you start with the graph. Do you see me writing?
Yes.
Thank you. So you start with marking off. So as soon as you see normally distributed, you put the curve with the mean of 68.6 and a standard deviation of 2.8. So you write that underneath on the graph. So find the percentage of men. So it's the same thing as probability of men. So you have the numbers, you want to find the probability. The first thing comes to your mind is normal CDF. So probability of men who are taller than a shower head at 72 inches. So 72 inches would be above this point or below this point if I want to eyeball it. So
Above.
72. This is 68. 72 is a little bit above because 68 here, 72 should be. But you want to know taller than 72. So taller than 72 means 72 or more. So that means you're looking for probability of the individuals that are taller than 72 inches. Greater than, that's the sign for greater than x, than 72. So then you would say, I want you to fill in before I fill it in because it's the same thing as we did. Lower, upper, mu, sigma. So lower 72. Upper is unknown, so I go 9999 or 10,000, whatever, a large number. Mu is 68.6. And sigma, the last one, is 2.8. You just put that to your calculator and that gives you the probability. So let's do it. Great. I see you got the answer. Excellent job. So let's just clear everything to have a nice platform. So we go to normal CDF. Then you would have 72. Tell me if I'm typing, though I go off memory. 68.6. What was the standard deviation?
2.8.
2.8. Okay, and if your calculator doesn't have the layout, so you would say 72, comma, 9999, comma, 68.6, comma, 2.8. Okay, and that's the percentage. So there are 11% of people that are taller than 72 inches. So if they want to cover more than like 95%, then this is not a good number. Maybe they need to make the shower heads a little bit taller. Because 11% of the community of men will not fit in that shower head height. Yes, great. Okay. So here we go. So we found it using technology. 0.1123. The proportion of men taller than 72 inches is 0.1123. That is about 11%. So 11% of men may find the design to be unsuitable. Any question? Okay, let's do another example. Finding values from known areas. That was with the inverse norm. So I just want you to distinguish between the two. Sometimes percentage or area is given and you find X, and sometimes the X is given and you find the area. Okay, let's do an example. Okay, this is a good one. I see a question. Oh, that's fine. Thank you for letting me know. Okay. Can someone please read this one? Can I get a volunteer to please read this one?
Yeah.
Okay, go ahead.
When designing equipment, one common criterion is to use a design that accommodates 95% of a population. We have seen that only 46% of women satisfy the height requirements for U.S. Air Force pilots. What would the maximum acceptable height of a woman if the requirements were to change to allow the shortest 95% of women to be pilots? That is, find the 95th percentile heights of women. Assume the heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. In addition to the maximum allowable height, should there also be a minimum required height? Why?
Thanks. Okay. So I want you to write down or graph things that you can understand from this one. So the shortest 95%. So what would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? So think about it. So they don't allow short pilots or they don't allow tall women pilots. Which one? First, let's just identify that.
They don't allow short pilots.
So they don't allow short pilots. So that means, so let's just have, oops. Let's just have the graph. Let's use the next page. So it says shortest 95% of women. So what does that mean? Shortest 95% of women. That means if it's a bell curve, you are fine with the shortest 95% of women. So you want to find what is this height requirements if they are allowing 95% of women to fit in. So you have the area. So area of lower. So area of lower, comma mu, comma sigma. That's going to give you x. So area of lower, they said the shortest 95%. So that's 0.95. Mu is 63.7. That was given in the problem. And also sigma was given. What was the sigma? So I'm writing on the page. I cannot.
2.9.
What is it?
2.9.
2.9. Now I want you to use your calculator. And then since you already have the area and you want to find x, you use inverse norm. So inverse norm is when you have the area and you are looking for x or z. So use your calculator, 0.95, 63.7, 2.9. Let me use my calculator as well. So second vars, inverse norm. Always you put area of lower, 0.95. Mu, was it 63.7? What was the mu?
63.7.
Yeah. So 63.7. And what was the sigma? 2.9.
9.
Thanks. Okay. So, and then again, if your calculator doesn't have the layout, 0.95, comma, 63.7, comma, 2.9. 68.47 inches. So the outcome of here, the outcome of this one is the x, is not probability. Inverse norm, you put in the probability, you get x out. So that being said, 68.47 Okay. They did multiple ways. Okay, a requirement of height of less than 68.5 inches would allow 95% of women to be eligible as US Air Force pilots. There should be a minimum height requirement so that the pilot can easily reach all the controls. Okay. Any question? You leave area as 0.95. Let's do another one. Oops. So let's go, let's go pick problems from the textbook now. Or from the worksheet. Give me a second. Let me stop sharing, going to the worksheet. Let me stop recording or Zoom recording.
I'm going to talk about the central limit theorem, including 4 important aspects. This video complements our video
So you hear it, everyone, right? Anyone has problem hearing the video? No? Good. Let's do it.
calculating a confidence. Statistics Learning Center presents Understanding the Central Limit Theorem. Hi, I'm Dr. Nick, and I'm going to talk about the central limit theorem, including 4 important aspects. This video complements our video calculating a confidence interval for a mean using a formula. It would also be useful to watch our video Understanding the Normal Distribution. The central limit theorem was first suggested several centuries ago, and many traditional statistical tests and procedures are based on it. The central limit theorem is concerned with the sampling distribution of the mean. The sampling distribution is the distribution of means of samples taken from a population. Usually, we do not know the mean of the population, so we take one sample. We use what we know or find out from that sample to make an inference about the mean of the population. We use the mean of the sample, x bar, the size of the sample, n, and the standard deviation of the sample, s. I'm going to talk about 4 aspects of the central limit theorem. Aspect 1. The sampling distribution of the mean will be less spread than the values in the population from which the sample is drawn. Aspect 2. The sampling distribution will be well modelled by a normal distribution. Aspect 3. The spread of the sampling distribution is related to the spread of the population values. Aspect 4. Bigger samples lead to a smaller spread in the sampling distribution. I will now illustrate these aspects with an example. We have a population of dragons and we wish to know their mean strength in order to tell whether the change in climate is affecting them. We want to compare that with information from previous scientific studies of the dragons. Each dragon is represented by one of these data cards. From experience, we know that the range of dragon strengths goes from 1 to 8. There are 720 dragons in the population, and we're taking a sample of 4 dragons. These are very small samples, but are useful for illustrative purposes. How likely is it that the average strength of the 4 dragons will be 1? You are right, it is very unlikely. All 4 dragons would need to have a strength of 1 for the mean strength to be 1. If there are equal numbers of dragons at each strength, then the probability of getting 4 dragons of strength 1 is 1/8 to the power of 4, which equals 0.00024, or 1 chance in 4,096. Similarly, it is very unlikely that the mean strength will be 8, as all 4 dragons would need to have a strength of 8. Let us take some samples of our dragons and see what the mean strength is for each sample. Here's our first sample. The mean is 4.25. And here is another sample. The mean is 5.25. And here's another sample. The mean is 4.75. And here are a few more samples. The means are 6, 5, 3.5, and 4.5. It could take a long time doing this by hand, so let's set up our computer to simulate taking 4,000 samples of 4 dragons from our population. We can only do this because we happen to know all about the dragon's strengths, having made them up in the first place. This is a simulation. We would never know this in a real-life study. Here is the distribution of those 4,000 means from samples of 4 dragons. Let's look at the 4 aspects mentioned before. Aspect 1. The sampling distribution will be less spread than the population from which it is drawn. You can see that most of the sample means lie between 3 and 6, and all of them lie between 1.75 and 7.5. Remember, the population values lie between 1 and 8. Aspect 2. The sampling distribution will be well modelled by a normal distribution. You can see that even with samples of size 4, that the distribution resembles a normal distribution with a bell shape. If we take larger samples, the distribution gets closer in shape to a normal distribution. Here are graphs showing the spread of sample means of dragons from samples of size 16 and 50. You can see that the shape is getting more like the normal distribution. This is also shown in our video about the normal distribution. Aspect 3. The spread of the sampling distribution is related to the spread of the values in the population. Say a different dragon population had a spread of strengths of 1 to 20 instead of 1 to 8. You would expect the spread of the sample means to be greater. Here is a graph showing the spread of sample means from samples of size 4 from a different population of dragons. These dragons have strengths evenly spread between 1 and 20. You can see that there is still the bell shape, but for these dragons most of the sample means lie between 6 and 16. Aspect 4. Bigger samples lead to a smaller spread in the sampling distribution. The bigger the sample, the less likely it is that all of the values will be small or that all of the values will be large, so that the chance of extreme values is reduced. Here is a graph showing the spread of sample means of strengths of dragons from samples of size 25. And here is a graph showing the spread of sample means of strengths of dragons from samples of size 50. You can see that the spread reduces as the sample size increases. The spread of the sampling distribution is related to the square root of the sample size. 2 important notes. You only ever take one sample from a population. We took thousands of samples to illustrate what a sampling distribution looks like. The central limit theorem only works under some conditions and with big enough sample sizes. 4 is actually far too small, though you could still see the effect. Under most conditions, samples of 30 are sufficient. This video was brought to you by Statistics Learning Centre. Subscribe to our channel and visit our website for more resources to help you learn.
Okay, before going to the PowerPoint, I want you to listen to the question I'm asking you, and then let's just think about this as we move on. So let's say DVC has 20,000 students, and you want to find average age of the students at DVC. It's almost impossible to have access to the computer, get their ages out if they release their ages, and then find the average. So that calls a census. So that's basically not doable. So then you think of taking samples. If you take one sample from DVC, let's say one sample of 20 students and find their average age, is that a good representation of the DVC students? So probably not. But then now you come and take many samples of 20s. That's central limit theorems. Central limit theorems, and then there's a minimum of 30. So, but then even with 20, so you go like 20, 30, 40, 50 of these samples of 20, you get average of all these ages. So average of these 20 people, average of these 20 people, average of these 20 people. The average of averages will be DVC students' age average. So which one is more accurate now? If you take bigger sample sizes or smaller sample sizes. So if you pick groups of 5s and you find the average and put it on a graph, or groups of 40 and find the average and put it on the graph. So larger sample size or smaller sample size, which one would be more accurate for samples of samples? Do you have any idea? Which one will give you a nicer outcome? Larger sample sizes or smaller sample sizes? Very good. It's going to be larger. The larger the sample size, the better representative of the population. So now let's go to the PowerPoint. Okay. The key concept is central limit theorem. Allows us to normalize the distribution. So we are normalizing, even if it's not normal, as you saw the dragon's strength. So it was something like with bumps, and then after you find means of means, you got something bell-shaped. So please write this part in your notes as we're going to use it. Central limit theorem for all samples of same size n to be greater than 30. Did you see that the lady was taking samples of 4? I said, let's take 20 students at a time and get thousands of those 20 student samples. To get the best results for central limit theorem, the minimum is sample sizes of 30. Means you pick 30 dragons and find their strength, or 30 students and then find many of those, another 30, another 30, another random 30. 30 or more than 30. The sampling distribution of X bar can be approximated by a normal distribution with a mean to be mu and a standard deviation to be sigma over square root of n. So the larger the denominator, the smaller the standard deviation. So as n gets larger, then this becomes a smaller because you're dividing sigma by a large number. So the whole thing becomes a small, so standard deviation becomes a small. If you have a graph with a smaller standard deviation, it's more condensed around the center. So that's why with large n is a better estimate. Okay, so please write that when you are talking about central limit theorem, n should be greater than 30. And then mu is mu, but sigma should be sigma over square root of n. So what you put in your calculator instead of sigma would be sigma over root n. Okay. If you have mu and sigma, then you need to make sure n is greater than 30. Mu is same as mu, but sigma needs to be sigma over root n. You don't need the conversion of z-score. Just mu and sigma over root n. Okay. If it's less than 30 or less than or equal to 30, then it's not a good approximation using central limit theorem. Okay, you check the requirements. You need to make sure n is greater than 30. And then you need to make sure that you let sigma to be, your new sigma needs to be sigma over root n. And mu to be mu of x bar to be mu, and n to be greater than 30. That's a summary of requirements to check. Okay. And here's another summary of that. There we go. Let's do an example. Can someone please read this one? The elevator.
I read.
Quick, go ahead, please.
Example, safe loading of elevators. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds per 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. A, find the probability that one randomly selected adult male has a weight greater than 148 pounds. B, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds.
Thank you. So just 4,027 passengers. So that this converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Assume that adult males have the weights that are normally distributed with a mean of 189 and a standard deviation of 39. Okay, mean of 189 and a standard deviation of 39. Find the probability that one randomly selected adult male has a weight greater than 148. So for the first part, it's nothing to do with central limit theorem because you are randomly selecting one person. Okay, so you would say, you write the middle. So mu is mean of 189 and a standard deviation of 39. Find one randomly selected adult, find the probability that one randomly selected adult male has a weight that is greater than 148. So 148 should be somewhere here. You eyeball it. What command do I use here?
Normal CDF.
Normal CDF. So you would say normal CDF. Lower is 148, upper is 999, 189, and 39. So please find that. And tell me what number you get. So put it to your calculator. Normal CDF 148, 999, 189, 39. Again, that's not the central limit theorem yet because you are selecting one. So I see some of you are already answering. Great. So let's just help me to put it in my calculator. So you would say normal CDF. That starts from 148. Help me with the numbers. I'm just a couple of nines. Mu, what was it? 180,
9.
189. And then what is the standard deviation?
39.
39. Okay. So paste. Okay, 0.8534. If you randomly select an adult, there's an about 85% chance that that male adult. They use male because they imagine the worst case scenario where males' weight tend to be higher than females' weight. That's why they say, like, let's imagine that everyone in there it's a male. So, but there is an 85% chance if you randomly select one person, that male be heavier than 148 pounds. Okay, so now to the second part. Oops. So for the first part, we got 0.8531 using our calculators. Okay, perfect. So now for the second part, it says, find the probability that a sample of 27 randomly selected adults, males, has a mean weight greater than 148 pounds. So now this time you're 27 randomly selected adults. It's not one anymore. Maybe that's one key point that you know it's you're using central limit theorem. And I'm going to write CLT, central limit theorem, where you are selecting 27. Of course, it was better if you had the number over 30, but we still continue. Okay, so first, you would say, make it bigger. We'll go to OneNote. Okay, in the OneNote, I'm going to write it. So you would say sigma. If I want to normalize it, if I want to use central limit theorem, the new sigma is the old sigma over square root of n. So it was sigma over square root of n. What was the sigma of man? 39? What was the, yes?
Yeah, it was 39.
Okay, so 39 over root 27. Use your calculator and find that number or use the exact. So now you would say normal CDF. So here's the graph. In the middle is mu, we said. So mu is, the mean of male is 189. Was it 189?
Yes.
And then sigma of the central limit theorem, because we are picking more than one, so we need to divide it by square root of n. So that's 39 over root 27, or if you are using decimal, please use multiple digits. So now 148 or more. Find the probability of average of their weight of those 27 people. You find their average and their average to be greater than 148. So then you go normal CDF. You would say lower, upper is going forever, mu 189, and then sigma, it should be the new sigma. We have 39 over root 27. So let's use that and put it to your calculator. So 148 comma, so I'm going to clear here. So you would say normal CDF 148, comma 999, comma 189. And now instead of 39, you would say 39 over square root of 27. Oops. Close the parentheses. Okay. Or if your calculator is one of the ones that you need to type, 148, comma 999, comma 189, comma 39 over 27. Okay. And that's almost 100%. That's about 1. It's pretty certain that if you randomly select 27 males, their weight will be more than 148. So that means the elevator will not be safe. Okay. So DC 0.99. We are quite sure that 27 randomly selected adult males have a weight that is greater than 148. So it's about 100% sure.
Professor, I had a question.
Yes.
So I thought with the central limit theorem, the n sample size had to be at least 30 or greater. But with this one, it was 27. So does it just need to be close to 30 or?
No, it has to be for using central limit theorem. We say the requirement is 30 to have the best result. But at the beginning of the question, I said we use central limit theorem for these type of questions regardless, although it's the most accurate when it's greater than 30.
Okay,
But,
got it.
but even when you saw in the video, even putting 4s, did you see when she picked a sample of 4 still was a good outcome. But then as n got bigger and bigger, then the number got closer and closer to the actual value. But when it's above 30, it's certain that you have the best outcome.
Got it. So 30 just, anything over 30 just gives you the most accurate answer.
Exactly. So given that the safe capacity of elevator is 4,000, it's almost certain that it will be overweight if it is filled with 27 randomly selected adult males. So in worst case scenario, if all 27 in there are males, so you're sure that this is overweight and not probably as safe as you're expecting it to be. Okay. And that's how you can now think about how they are designing elevators or height of shower or height of doors. And they make sure that majority of people fit, or if it's safety, they would say, okay, the heaviest part of the population will also fit, and so forth. Okay, let's do this one. So I'm going to give you 2 minutes. Read the question and see if you can graph it. So see if you can graph a bell shape. Mark the middle mu, and then the sigma. If n is anything more than 1, then you need to come up with sigma of whatever over square root of whatever. You need to identify that. Then you need to shade the area and then use normal CDF. So I'm going to give you 2 minutes. See the question, see if you can set it up and get the right answer, and send me your answers. Okay, so now let's just it's assume that the population of body temperature has a mean of 98.6. So regardless if you're randomly selecting one or more, mu is 98.6. Is commonly believed. Also assume that the population standard deviation is 0.62, but then now you're taking a sample of 106. This time is greater than 30. But regardless, we use it 0.62 divided by square root of 106. Find the probability of getting a mean greater than 98.2. So 98.2 is probably somewhere here. So you would say normal CDF, 98.2, comma, going forever, 999, mu 98. I don't know why my pen is not writing on it. 98.6, comma, 0.62 over root 106, close parentheses. So I'm going to use that on my calculator. So let's go here. I'm going to go second distribution. So the lower is 98. Was it 0.2? The average was, yeah. Was it?
Yes.
And then the mean was 98.6. Yes? I haven't memorized the numbers if someone can help me. 98.6 was the average. 0.62 over 106. 0.62 over square root of 106. Okay, did I type it correctly? Lower 98.2, upper 999, 98.6, 0.62 divided by 106. Okay, or use commas. So that's 1. So that's pretty certain as well. So 0.982. And then you said body temperature that is greater, right? Did we say getting, oh, that is, or lower, sorry. That says getting a mean of 98.2 or lower. So 98.2 or lower, did I, oops, give me a second. 98.2 or lower. So that means you shade the lower part of the graph. So that would be, let me open OneNote. So here it is. If you had the curve, I was not paying attention. So you would have mu in the middle. Mu is 98.2, so 98.6. Sigma, we said it's 0.62 over square root of n, which n was 106. And then the temperature to be 98.2 or lower. So, or lower, that means you have negative 999, so normal CDF, negative 999, comma, 98.2, comma, 98.6, comma, 0.62 over root 106. So this one, now it's good. So now putting it in our calculator, so that is 98, that's negative 999. So I go to, oops. So I go to second vars, normal CDF, -999, upper to be
98.2.
98.2, mu 98.6, 0.62 over root 106, and then pace. Okay, that's about 0. So do you see it says e to power -11? That's like 10 to power -11 with scientific notation. You go backward 11 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and you drop the decimal, and you're going to have 0 for all of them. So this is almost 0. So it's almost impossible that healthy adults with the lower temperature than 98.2. Okay. So let's go here. So you find the sigma, you find the area. So they have the area like with 3 zeros, but ours is more accurate because we are using calculator. So it's almost 0. So the result shows that the mean body temperature is really 98.6 as we assume. There is extremely a small probability of getting a sample of 98.2 for 106 subjects. Okay. So any question? Okay. So that's all for today's lesson. Homework is up. Please do the worksheet for chapter 5 and 6 tonight. And also homework for MyMathLab is up, although it's due tomorrow night. I highly suggest that you do it as soon as possible, or at least get it started. Remember, summer courses are flying so fast. So worksheet 5, worksheet 6, and then start MyMathLab work. Have a great time. See you tomorrow.
Thank you, Professor.
You're welcome.
Professor, on that last question.